Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video to those that need it. You may also love to click on the notification bell so that anytime I upload a new content, you'll be duly notified. I want to use this medium to thank you all for having confidence in me. I am very grateful, and I pray that God will grant you all success in your physics internal and external examinations. I promise to make a video on HOOKE'S law. You may love to click in the description box below to get a video link on the theory of HOOKE'S law. HOOKE'S law is one of the topics examiners love setting questions in. As a student, you can't escape questions from this topic. I'm telling you what I know. So I encourage you watch all the video series. In this video, we want to concentrate on calculations. Please watch all the videos so you can get set for your exams. So without wasting much time, I would like us to go straight to the business of the day. You also love to click in the description box below. I have a link to this document in case you may need it. So let's go straight to the point. A spiral spring extends from a length of 10.00 cm to 10.01 cm. When a force of 20 Newton is applied on it. Calculate the force constant of the spring. Before we proceed on these calculations, there are first things first that you need to pay much attention to. Calculations are not done randomly in physics. They follow an algorithm. They follow a logic sequence. So this is what I call the 5 C's of calculations. When examiners want to mark your scripts, they want to look at these things. The first C stands for, that is the 5 C's. The 5 C's for calculations in physics. The first C stands for correct data collection. The second C, the first C stands for correct data collection. Second C, correct equation, correct substitution, correct evaluation, correct answer with SI unit, if any. It means that after you are done calculating, there are some answers that don't have SI units. So if you put SI unit, you are wrong. Relative density is a dimensionless quantity with no SI units. When you are done calculating relative density, you need to put your answer. Mechanical advantage, velocity ratio, strain, all of these, they don't have SI units. So if you are done calculating and you put the SI units, the examiners will mark you down. So that's what I mean by the 5 C's of calculation in physics. So let us collect our data. First off, we have the length. We have the length L, let me say the original length of the spring to be 10.00 cm. You have to convert this to standard unit, that is to meters. That by 100 will give you 0.1 meters, I suppose. Let me just confirm that 10 divided by 100. Yes, I was correct. And so the second one is the extension, let's call it L. The extension L is 10.01 cm, and that to 10.01 to meters. 10.01, and this will give us 0.1001 meters. And so the extension is given to be the actual extension, the real extension is this length minus L naught, and that is 0.1001 minus 0.1 meters, and that would be our extension, minus 0.1 minus 0.1. So our extension is 0.0001 meters. That is the extension. So the force F is given to be 20 Newton. So they are asking us to find the stiffness of the material, the elastic constant. So the next thing is to state the correct equation you want to use to solve this equation. So you write out F is equal to KE, and then you make K the sum of the formula. So this implies that K is equal to F all over E. So this implies that our K is given to be 20 Newton divided by 0.0001 meters. So if we do that correctly, we have 20 divided by 0.0001. We have our answer to be 0.00000 Newton per meter square. So therefore our K is given to be 200,000. That is 200,000 Newton per meter. That is the correct answer. 1, 2, 3, 4, 5. As simple as A is C. So let me wrap it up. We want to look at the next question. It reads, a force of 1.8 Newton extends the wire by 0.4 cm. What force will extend the wire by 1.25 cm if the elastic limit is not exceeded? This is a NECO question, as simple as ABC. So applying the 5 C's of calculation in physics, we do the same thing here. So we write that we have two forces here. This force and then the action of the second force. So we also have two extensions here. So this is what we're going to write. We write that our F1, which is the first force, our F1 is given to be 1.8 Newton. Good. Our F1 is 1.8 Newton. And E1 is given to be 0.4 cm. And that to meters, 0.4 to meters, 0.4, that will give us 0.004 meters. And our F2 is not given. Our E2 is given to be 1.25 cm. That to me is 1.25 divided by 100. That will give us 0.0125 meters. And so they are asking us to find the force, the F2. But you see, the elastic limits of the material is not given. The stiffness of the wire or the spring is not given. And this is the nature of physics questions. You have to break the bone before you get to the marrow. So you have to find this. And again, the elastic constant for the material is the same throughout the whole process. So write that we use our F1 is equals to KE1. So make K the subject of the formula. So write that this implies that K is equals to F1 divided by E1. So this implies that our K is equals to F1 is 1.8 Newton divided by E1. Your E1 is 0.004 meters. So if you evaluate correctly, we have 1.8 divided by 0.004. Good. If we do that correctly, we have 450 Newton. Newton what? Newton per meter. This is the stiffness of the material. So at this point, we can use this to find our F2. So our F2 is equal to KE2. So this implies that our F2 is equal to 450 Newton per meter times our E2. We have 0.0125 meters. This meter will come on this meter. And then you are left with 450 times 0.0125. 0.0125. We have 5.625 Newton. Therefore, our F2 is this. As simple as ABC. Now, to this, we have come to the end of this particular video series. Follow me up in the next video series if you love this calculation, so that we can finish all the calculations in physics in this topic. Don't forget to subscribe, like, comment, and share. God bless you. Bye-bye.